All right, I think it's time to start. Welcome, everyone. Nice to see you again virtually. Maybe I should say a few words about this session. We have three sessions on the topic of mesh adaptation techniques for numerical simulation. What happened here was that Suzanne and I proposed something with a similar title back, last year when we thought this would all be in person. And then I think when it was announced, we saw that Frank and Adrian also had something very similar. So we said, let's just join the two symposia together to one big one. Pretty generic. We are looking forward to more mesh focused talks as well as more simulation focused. But of course, the common theme would be that it's about any type of numerical simulation with something mesh and adaptivity related. And you'll see that it's a pretty diverse set of talks we have here. So that's it. And we all know how this procedure works. So I think we can get started from the top here. I hope you can see my PDF with the 5 talks that we have now. I should say though, but I can say that later again, but our last speaker, Weixiang Huang, mentioned that he might not be here for the question and answer session, but we'll make it to the next one, the next session, so we can do those questions and then maybe. But we can bring that back when we get there. So let's get started. Our first speaker is Martin Bergen, going to talk about a new shape calculus for cut FEM discretizations.
In the case of shape optimization, a very natural way to effectuate shape changes is through domain transformations using a so-called velocity field V. There will be one velocity field associated with each design variable. The velocity field can be used to move the mesh points to create a deformed mesh that conforms to the transformed computational domain. The velocity field enters when calculating shape derivatives of integrals. If the function f in the integrand is smooth enough, it turns out that the shape derivative of a volume integral only depends on the normal flux of the velocity field at the boundary. This is very convenient computationally. The complication here is that the function f often is not smooth. For instance, when f is the integrand of the stiffness matrix in a finite element discretization, the use of the divergence theorem is not really justified. Thus, the use of the boundary formulations of shape derivatives in the context of finite element discretizations generate inaccurate gradient directions. Mesh deformations, however, are somewhat of a practical hassle, particularly in 3D. Recently, we have had very good experiences from using the cut finite element technique for shape optimization. Here, the computational mesh is not deformed. It is fixed within a so-called hold-all domain D, and the boundary of the actual domain of interest is allowed to cut arbitrarily through D. All calculations are done in the fixed hold-all domain, and the boundary of the domain of interest is an interior boundary to D. We use a finite element level set function phi to specify the location of the domain boundary. Shape changes are done through perturbations of the basis functions of phi. So there are no domain transformations, no velocity fields, and no mesh deformations. The standard sensitivity analysis is not a good fit to this situation. What I suggest is an alternative analysis based on a generalization of an approach recently proposed by Delfour. This approach does not use transformations, but dilations into Euclidean space of lower dimensional objects like points, curves, or surfaces. A perturbation of the level set function generates a dilation ET of the part of the domain boundary that intersects with the support of the basis function. The analysis reveals that the shape derivative here has a convenient representation in terms of a boundary integral. As opposed to when mesh deformations are used, this representation is exact for the objective function, even when the integrand contains jump discontinuities. Thus, this boundary formula yields accurate gradient directions, something that the boundary formula cannot achieve when mesh deformations are used. We have used the shape derivatives that came out of such an analysis to optimize the shape of a so-called phase plug of a compression driver. A compression driver is a standard sound source for acoustic horns used in outdoor live audio settings. The interior of the driver is tricky to design to avoid resonance and interference effects. Mathematical model is the Helmholtz equation for the acoustic pressure, complemented with a somewhat complicated boundary condition modeling viscothermal boundary layer losses. Using the cut finite element method and a quasi-Newton algorithm to modify the level set function that defines the wall of the phase plug, we managed to find the shape that could match the frequency response of a mathematically ideal compression driver. Thus, to summarize, the traditional shape calculus is built on domain transformations. This is a very natural approach when mesh deformations are used, but not a good fit to cut finite element methods. The shape calculus based on dilations, however, fits very well to cut finite elements. Such a calculus leads to the somewhat surprising conclusion that there is an exact boundary representation for the shape gradient, also in the low regularity case of finite element discretizations. Thank you.
All right, thank you, Martin. And while they switch to the next talk, I can read it out here. If I can pronounce the name correctly, sorry if I do not. Ugo Digone, speaking about massively parallel anisotropic mesh adaptation applied to Earth-land elevation.
So hello everyone, welcome to this online presentation. I will talk about my work on massively parallel anisotropic mesh adaptation applied to Earth-land elevation. I'm Hugues Digonnet from the HPC Institute of École Centrale de Nantes. So in this work I want to combine mesh adaptation and supercomputer power. So the main goal for that is to reduce the computing time. So both from mesh adaptation to reduce the discrete problem size for a given accuracy. So here you can see on this picture we have some small elements where we have details, and we have bigger anisotropic elements quite far from the details. And also we want to take advantage of supercomputer that increase quite a lot the computational power and using a large amount of core. So combining supercomputer and mesh adaptation that will enable us to make some large-scale simulations. So first, some parallel performance about the mesh adaptation we have made. So it was weak speed-up test up to full tier 0 supercomputer scale and ending with 77,000 cores on Curie. And the goal of that was to build largest mesh with more than 1,000 billion elements. So here are the characteristics of these meshes in 2D and 3D. So we use 77,000 cores. We made a mesh with more than 1,000 billion elements with a good quality, a number of neighbors that are still quite low compared to the number of core used, so that's good for parallel computing, and the time to make that, and also the output. So just outputting the mesh take about 40 terabytes and was writing on the disk at close to 100 gigabytes per second. So after that we want to apply this anisotropic mesh adaptation strategy to well capture land elevation at Earth scale. So we take a data set with a high resolution, 3 arc seconds. It's a huge data set, 14 gigabytes of compressed data, more than 10 times that uncompressed. The sea level is not present in the data set, and also the poles are not present. So we use a coarse data set resolution at poles to complete this one. So here it's an example of one of the subfigure close to Nantes to have an idea of the precision of this data set. So using that data set and parallel computing, we have been able to build a final anisotropic adapted mesh in 3D using 8 kilocores, and this final mesh contains around 7 billion nodes and 40 billion elements. So this is an image of the Earth with land elevation, so Himalayas, Alps, and so on. And if we make a zoom on Himalayas, we can see here on the left the Indus Valley, and also if we make a zoom on this Manga Barabat mountains, we can plot also the mesh to see what kind of mesh, adapted mesh, we obtain on this, and we have these details everywhere at Earth scale. So to conclude, we have been able to execute mesh adaptation at full tier 0 supercomputer scale. The largest meshes we have generated have more than 1,000 billion elements in 2D and 3D, and using 77,000 cores and more than 200 terabytes of RAM. Combining anisotropic mesh adaptation with supercomputer power allow us to well represent land elevation with a high resolution dataset at Earth scale. And thanks also to a visit, we have been able to visualize such huge meshes in high resolution. And ongoing works, we are looking to exascale supercomputer with new architecture, ARM core, GPU, and or using several million core. And also we want to combine optimization, so mesh adaptation with supercomputer power, but also with high order element, with multi-grid solver to reach very large scale simulations. Thank you for your attention.
All right, thank you. Heading over to our third talk. It will be given by Vladimir Garanza about the topic of moving deforming mesh techniques for fluid flow simulation with immersed boundary conditions.
Dear colleagues, I'm glad to present a talk on moving deforming mesh technique for fluid flow simulations with immersed boundary conditions. The main idea of this work is to deform fixed connectivity mesh to make condensation zones precisely follow the moving boundaries in order to improve accuracy of immersed boundary conditions for the Noisette flow solver. The mesh deformation strategy is based on the 20-year-old paper by Garanza. In order to compute mesh deformation, we use stored energy based on the sum of shape distortion and volumetric distortion. It builds a mapping between the manifolds with metric, and metric tensor Gx define the mesh movement. After finite element discretization, we get a discrete function as a function of position of mesh vertices. And Hessian matrix is built of D by D blocks, and we extract from this matrix its positive definite part in order to get a stable minimization. We use a single iteration of Newton type method with 1D minimization in order to compute the displacement along the minimization directions. And we also restrict this displacement by 1.5 for simplest scheme in order to avoid to suppress mesh oscillations. We use incomplete Haletsky-based preconditioned conjugate gradient solver in order to compute the minimization direction. And also we use a two-step predictor corrector scheme, heuristic one, where the second linear solve is in practice based on the matrix from the first linear solve with its incomplete Ilyu factorization. These techniques allows to run with a very large steps and compute non-degenerate D+1 prismatic layers in space-time. And inside this layer, flow solver can use its own time-stepping strategy. In practice, one linear solve is sufficient for 5 to 6 linear solver flow solver time steps. The system of bodies is defined by CIMNE implicit function, and we define the compression factors. Sigma 1 is normal compression, and sigma 2 and sigma 3 or sigma 3 are tangential mesh compression factors. And there is a isotropic mesh layer and its pre-image in parametric domain. This is anisotropic mesh layer and its pre-image in parametric domain. This is a rotor configuration and geometrically adapted mesh. We use special adaptation in the high coverage zones. Those are fragments of mesh. We get a mesh which is almost periodic. So this is first and the second rotation. And this movie illustrates the mesh movement and deformation. This is the same mesh deformation in the rotated reference frame. This is again quasi-periodic behavior of the mesh deformation. This is a parallel domain decomposition technique and deformation of subdomains. And this is a deformation of subdomains in 3D. This is a mesh layer in 3D and its pre-image in the reference domain. This is a moving mesh layer in 3D, which precisely follows the controls. And the scalability of parallel mesh deformation algorithm is comparable or superior to that for implicit flow solver. And also there is a reasonably good match between computations results on hybrid boundary fitted mesh and adaptive mesh with immersive boundary conditions for Noisette solver. This is a 4-rotor configuration. And this is the vorticity field on this 4-rotor configuration computed using Noisette solver. Thank you for your attention.
All right, thank you, Vladimir. Heading over to our fourth talk by Johan Hoffman on the topic of adjoint-based mesh adaptation techniques for simulation of turbulent flow.
Hello everyone, my name is Johan Hoffman and this presentation is adjoint mesh adaptation techniques for simulation of turbulent flow. Turbulence is a highly localized phenomenon, which therefore opens for efficient mesh adaptation techniques. Here are 3 examples: flow past a car with an attached turbulent wake, flow past a landing gear with the turbulent separation, and flow past the high lift configuration of an airplane. So in all these cases, we've used adaptive finite element methods to compute a solution to the problem. The adaptive finite element method that we use is based on 3 parts. It's the goal-oriented mesh adaptation technique developed during the 90s. It is the residual-based turbulence modeling approach where we avoid empirical parameters. Instead, we base the turbulence models on the residual, that is the equations themselves. And we use slip boundary conditions to avoid boundary layer resolution. The goal-oriented adaptive mesh adaptation method is based on an a posteriori error estimate of the output error or the error in an output of interest M. And this error is bounded by a sum of error indicators of the mesh. So these local error indicators takes the form of a mesh size, the local mesh size, H, the residual, R, which measures the local error, and S, which is a stability weight, which is constructed from the solution of an adjoint equation, or the dual problem. So the algorithm goes as follows. We solve the primal problem, the Navier-Stokes equations. We solve the dual problem, the adjoint equations. We construct the error indicators, and we refine the mesh, or modify the mesh. In this case of the airplane, the ratio between the finest and the coarsest cell in the mesh is about 1 million. Here are 3 examples of adjoint fields, or snapshots of adjoint fields. For the car, we use an output of interest of drag, and for the airplane, both lift and drag, and for the landing gear, we use 2 different outputs of interest. At the top, it is the drag force, and at the bottom, it is the acoustic sources. So we measure the acoustic field at the distance from the landing gear. These methods are implemented in Phoenix, or more specifically on the Dolphin HPC platform, which is developed and maintained together with our collaborators and with the spin-off company Cloud. So strong scaling can be observed up to about 20,000 cores for these types of problems. Finally, some words about the stability of turbulence, or specifically turbulent incompressible flow. So we solve the adjoint equation in our adaptive algorithms, and we can also study perturbations in the perturbation equation, or the evolution of vorticity in a vorticity equation. All these equations describe the evolution of derivatives of some sort, and they have very similar stability properties. So the evolution of these derivatives or perturbations can be expressed in the form of the energy of such perturbations that experience viscous dissipation, but also production based on the velocity gradient. So the velocity gradient expresses the local stability of turbulent structures. And we find that even though turbulence in many respects is unstable or hard to predict phenomenon, it is composed of stable elements such as stable vortex tubes or linearly unstable shear layers. Exponentially unstable flow structures can only exist for a very short time, even in a turbulent flow. Thank you very much for your attention.
Okay, thank you, Johan. And now for our last talk by Weizhang Huang about phase field modeling of brittle fracture and its adaptive moving mesh solution.
First of all, I would like to thank the organizers for the invitation to this mini symposium. Today, I'm going to talk about the phase field modeling of brittle fracture. Brittle fracture is a fracture showing a little or no plastic deformation. It occurs rapidly and can be catastrophic in engineering practice. So it's very important to understand the initiation and propagation of the fracture. So for the numerical simulation of a brittle fracture, there are 2 common approaches. So for the variational approach of elastic modeling, without the crack, let the U be the displacement epsilon, the strength tensor, and then the energy can be obtained by the Hooke's law for isotropic material as like this. And then by minimizing the total energy, then we can find we can find a U. For the situation with the cracks, we can write the total energy into this the energy for the undamaged area, and this is for the damaged area. And GC is called the toughness of material. Is actually is the amount of energy needed to create a unit area of fractal surface. So for the phase field modeling, so we're going to define or use phase field variable to identify the cracks, because the phi is 0 on cracks, is 1 away from cracks. So then we can write the energy into this form, use the characteristic equation and delta function. So then I use called the CIMNE approach for the characteristic function by this continuous function, and also by this delta function by this discrete, we call it discrete or approximate delta function. Then we can approach, to approach the energy into this called CIMNE energy form. Unfortunately, and this does not work because it leads to force cracking. The reason is that the energy, that's not contributing to damage is also degraded. So one way to avoid this problem is to decompose the energy into active and passive components, and we only degrade the energy with the the active component. Commonly used model for the energy decomposition is called the spectral decomposition for energy. So the main idea here is that to decompose the strand tensor into two parts, the first part is a tensor part, another complex part. Then with these two parts, we can form the active energy. This will be a contributed damage. Then passive energy, this is not contribute to cracking. So then we have a total, a final CIMNE total energy like this way. So for the numerical solution of this problem, so the main challenge is that the first one is that the total energy actually continues, but unfortunately it's not smooth. So as a result, the Jacobi matrix may not exist at cracks, and the Newton iteration can fail to converge. So we propose the use regularization method. For example, we can use a sonic point regularization like this way. We prove that this method is very effective, improving the convergence of Newton iteration. So another problem is coming from the partial degradation at cracks. The force cracking too for some situation, because there's some still force level at the crack. So we propose to introduce the critical damage zone. Now we have 3 zones. One is undamaged zone, another one is partial damage zone, another one is fully or critically damaged zone. For this critical damage zone, then we use a full degradation. So total can take out all the stress. So then another issue is that, we're going to have a very sharp layer around cracks. So it's very natural to use a mesh adaptation to catch these cracks. So we use the MMPD adaptive moving mesh methods. So this is a shear test, situation. The first row showing the evolution of the cracks, which is the contour of phi. The detail of the work can be found in these 2 references. Thank you very much for your attention.
All right, thanks to all of our speakers very much. And I believe we can get started with the question and answer section. Again, let me remind you that this last speaker here, if you have questions, please, I hope many of you will make it to the session right after this one, starting at, I believe, 4:55, and then the last speaker will be there. But for the other 4 speakers, please send questions in the chat if you can. And we have a few coming in already. Vladimir, are you there? Would you like to respond to the question about describing more the passion to determine directions?
Hello, can you see me? Is it fine? the sound and the video? Okay.
I'm great. I see you well too. Yes, thank you.
Okay, nice to meet you. The question is, how can you use the Hessian to determine the direction for mesh movement? Yes, of course, yes, we do. We can use the Hessian, and actually, sometimes in order to use the curvature of the surface, we should use the Hessian of some implicit function, right? And extract the information about curvature. But one should take into account that for this particular problem that we're solving in this work, the normal compression and tangential compressions are quite very non-equivalent. So we can specify the normal compression using special law, but for target compressions, or we should use quite a tricky algorithms. So the Hessian can be used for adaptation, but we are not ready for adaptation yet. We try to make the mesh to follow very precisely the moving or deforming body, keeping in mind that compression is very large and global deformation can be very large. So this is the main problem for this talk. Okay, this is it.
Right. Thank you, Vladimir. Any follow-up? Yeah, looks like we resolved the question. We might come back to you. Don't go anywhere. But let's head over to Martin, if you're around.
Yes.
The question from Fredrik Lawson. Would you like to respond to it?
Yes, let's see. I presume the question was, I presume that the shape derivatives are used as data to a sensitivity problem for the sought field. Are there any particular issues related to the sensitivity problem in the CUT-FEM settings? Yes, I mean, actually, it's more issues for the if you move the mesh, then you may know that there are two expressions in the literature for the shape derivatives. One is a volume that involves the velocity field everywhere, and one is only at the boundary, which is more convenient. It turns out if you move the mesh, the boundary expression is not very accurate, even though it's used many times. But for the cut finite element method, since the mesh is moved, is fixed, it turns out that the boundary, there is an exact boundary expression for the gradient that is exact in the discrete case. So it's actually better in I would say, than it's better gradient. There are issues where you have corners in the cut when the domain cuts, you get these corners. You have to take that into account, particularly for boundary integrals. So the expression can be complicated, but there are strictly boundary expressions for the gradient, which is very nice, actually. It's an advantage with the cut finite element method. I hope that answers the question.
All right, thank you, Martin. We do have a question for the last speaker, Wei Zhang Huang. As I mentioned, I believe he's not here. No, so please, maybe we can forward or direct that question to the next session in about an hour from now, if possible. And I'd welcome questions from about any of the other talks. Maybe I can just ask right ahead since you're there, Martin. What about, I'm just curious about this. Can you get some of the benefits from cut cells? For example, one obvious benefit is that you could handle topology changes of the domain, right?
Yeah, well, yes, we don't do that yet. But one big issue is it seems less stiff. So we have done a lot of this acoustics optimization. And I believe, for instance, I believed that acoustic horns should be smooth, but they turn out they should not be smooth. So I thought the oscillation we saw I thought that was numerical issues. But with cut-out finite element method, it's more flexible in a sense, it turns out. And it turns out that sub-wavelength oscillations are beneficial for the performance. I didn't know that. And that came out due to it's more this level set description we have is less stiff than if we do some other kind of parameterization of the boundary.
I see.
So,
but I'm thinking that maybe you could do what the topology optimization people are doing. That you, for example, you bombard the domain with a lot of holes, and then the sensitivity directions will merge. Of course, you're going to need to do some magic merging. I mean, you're going to have to do some geometry modeling, right?
No, but the full technique we use now is actually you use the same sensitivity analysis for topological derivatives and for shape derivatives. We haven't used that yet, but that's another advantage, I think, that we can combine topological derivatives and shape derivatives in the same computations.
And because it's a fixed mesh and cut cell, maybe you don't need to do the horribly complex operations of merging when they collide, right?
Maybe.
Really.
Yeah.
All right, thank you. Let's see, we have some more questions. Suzanne is asking a question to Vladimir. Do you see it, Vladimir?
Yes, right.
Summary of key features.
Oh, sorry for compressing it. It's too much. I hope that the video is downloadable so you can read it slide by slide in the video. I don't have time to shorten it very much. The idea that we don't have a time-dependent principle in no moving mesh equations. So we have invented some heuristic procedure, and for us it was quite surprising that something which behaves a little bit like second-order Runge-Kutta scheme works very well for this problem without time derivatives. So this is for us the main surprise, and we still do not understand how it works. So this is heuristic part. From the point of view of rigorous foundations, we guarantee in this algorithm that we can have huge displacement on our mesh, which are space-time non-degenerate. So we create large space-time prismatic layers, right? And the flow solver can use these layers for its own time stepping, and generally the flow solver can do 5 to 6 time steps. They also use some kind of implicit procedure for that. And also what is important, well, of course it depends on the problem, because for some, if your movement of your body or deformation is quite wild, then you can, of course, you cannot use very large deformations with very large time stepping. So the idea that eventually we have created something which admits very large deformations is quite stable, and takes smaller time, computational time, compared to the flow solver. So it was a very important observation for us. Because compressions and mesh deformations in this technique is very large, actually, and for us it was a quite hard problem. About high order meshes, well, technically the answer is yes, because mathematics should not be changed here, but we didn't try it yet. So this is it.
I guess one thing with a high order would be that you mentioned something that you could take very large time steps with your little the technique with the little t, right, where you were able to take relatively large time steps. With high order, maybe that becomes the whole issue of untangling when they start wrapping around might become a bigger problem.
The idea that we completely avoid untangling here. So we create very large time steps. Just I think the implicit procedure here is very powerful and allows to create linear increments, just simple linear increments and very large time steps, because simpler procedures would not allow that. It's like I was doing a research on prismatic layers, creating prismatic layers with huge steps. Here we have a kind of prismatic layer with large steps in space-time. Well, efficiency, at least it's efficient enough for particular application. What about accuracy? Accuracy is responsibility of the author of the code, to tell us the truth. Because I am still a bit skeptical that this is a fully competitive approach, but they claim, there was a slide that these results are comparable to that for hybrid meshing, which is orthogonal and compressed near boundary. Well, I hope that them luck with these comparisons, but we are responsible only for meshing part. This is, in short, the review of the talk.
All right, makes sense. Thank you. All right, Johan, are you there? A question about the adjoints. Are you doing checkpointing or something? How do you store all the primal solutions?
Yeah, we do. We store snapshots and reconstruct by interpolation, but we store the full spatial field, which I think is very important, because as was shown briefly on the last slide, that's where all the stability, the main stability properties are driven by the velocity gradient. So I think it's very important to not smooth out that, but to store the full spatial representation of the field. So a short comment on that. The note I put in the chat is an analysis of that term, and we use this triple decomposition of the velocity gradient, which I wasn't really aware of that up till recently, and I don't know how well known it is, but it comes out of the flow visualization community. So instead of splitting the velocity gradient into the strain rate tensor and the spin tensor, you're actually able to extract the shear from that as well. So the problem with the main issue with the strain tensor and spin tensor is that it's not pure strain and it's not pure rotation, rigid body rotation, because both of them also involve shear. So in the stability context, that is problematic, and also if you want to visualize vortices, for example, in a turbulent flow. So that's all these different conditions to visualize vortices in a turbulent wake, for example, have to deal with this problem. So in a shear layer or a boundary layer, a laminar boundary layer, there is no rigid body rotation, but still there's a lot of vorticity, right? So, but with this decomposition, you actually split up the flow field into pure strain, pure shear, and pure rigid body rotation. So that also gives you a more refined analysis tool with respect to the stability of the adjoint problem or the perturbation problem or the vorticity equation. So you can analyze that more details. You have these three different types of stability. You have the rigid body, which is stable, so pure imaginary or eigenvalues, and you have the strain or elongation, where you have exponential growth or decay, and then you have the shear, which is a degenerate eigenvalues. So you have this linear growth. So you only have generalized eigenvalues. So that's a very neat way to get some more information out of that term, which really drives the stability properties of.
And why did you say that you store the entire spatial solution? Because of the sensitivity of these terms that.
Yes. I mean, I store at a certain frequency depending on how much data you want to store or that particular computing environment, but the full spatial field to be able to represent the full spatial gradient. Yeah. So you don't project to a coarser mesh or something to say.
Oh yeah, that would be an extreme. Yeah, that's true.
Yeah.
But may I add here? Yeah. You don't, as I understand it, you don't see exponential growth of the adjoint then, as has been reported from many people.
Yeah, so that's part of this. So we have never seen that in the fully developed.
It is. I have seen it. I've seen at least seen other people reporting it. So how
Yeah.
would you...
So what? So to that I have a few. One thing is that the discrete adjoint. I don't know if that was the case. I don't know how. That's another thing. I'm talking about the continuous adjoint, and then when I've seen it published, I've only seen it in the cases, for example, 2D bluff body problems at higher Reynolds numbers. So which published cases do you mean more specifically?
Have you seen it in a channel flow at high 3D channel flow at high Reynolds numbers?
Yeah, but
so turbulent.
Yeah, but if it is an unstable flow, then this is fine. But if you compute the wake flow behind the car, for example, then that wake is very stable, and the actual turbulent wake is just a dissipative sink, really.
Okay.
And so we of course it's not a small adjoint problem, but it doesn't explode. It highlights the turbulent wake, but it also highlights the backward, the upstream.
The argument is that if you have a transition scenario, so it's chaotic, and then the adjoint will be exponentially growing.
Exactly.
Yeah. Okay.
And
So you don't disagree with that then?
No. Then it does what it should, and also the perturbation equation shows this. Yeah. But there are. Sorry, yeah.
If the adjoint was exploding exponentially, basically, I mean, it's not wrong. It just means that the physical that is too sensitive to predict anything, and it would be worthless, right?
Yeah, and it's linearized around the base flow, which is unstable.
Exactly. Yeah.
But in these cases where you have a fairly stable turbulent wake behind a car or an airplane, then that flow field is in fact really stable, unless you zoom into these turbulent vortices. Well, actually, the vortices are stable, but it's more like these saddle points where you have the strain elements. And if you analyze this, visualize these kind of turbulent fields, that's where I saw this triple decomposition first. You see that these vortices are fairly stable. You have shear flow that either rolls up into stable vortices or it dissipates. And then you have these saddle points or strain fields are just popping up and disappearing in intermittent bursts, but they cannot exist for any.
And which is the thing that you said you got inspired by the flow visualization community?
Yes, it's called a triple decomposition of the velocity gradient. So what you do is that you first rotate the flow field in a direction that you can subtract the shear, because the shear acts in one plane, right? So, and then the remaining, what you have then is a tensor where you have subtracted the shear, and this you can then divide into a symmetric and skew symmetric part, which then is free from shear.
Cool.
So all the references are in this paper I put in the chat.
Yeah, great, thank you. All right, let's head on to see if our speaker, Hugo Digonet, are you there? We have two questions lined up.
Yes, can you hear me?
Yes, it's very distorted though. But I think it's fine.
Can you hear me better right now? No.
I think it works. It's good volume. It's fine. It's just a little noisy.
Let's see. I can do better.
But I think it got better right there.
Is it better right now or not?
Now it's really good, I think.
Okay. So to answer the question of Mozart about is it one-shot mesh adaptation at full Earth scale? It could be, but it will be not efficient in parallel. So yeah, we split the computation into several sets to enrich progressively the mesh to reach this final definition. So depending on the mesh size we want, we use more or less CPU cores.
Makes sense.
Maybe if I go through the question about Suzanne and the communication model, I don't know if it's the question or not, but we used classical MPI library to make parallel computing. And as we keep a number of neighbors quite low, it works quite fine, up to several thousand cores. The only problem we are facing right now is that full supercomputer size, the memory footprint of the MPI unit seems to be very costly. It takes close to 25–30% of the full memory available on the computer. So that need to be improved maybe.
Can I ask you a very more big picture thing here? To me, I was shocked about the size of these systems. I mean, I think I've heard finite difference people without storing meshes or nodes doing on the order of 1,000 billion degrees of freedom, right? But I don't think, I mean, do you know, has anyone done anything remotely close to this with fully unstructured meshes?
I'm not really sure. With structured or hierarchical meshes, yes, but with fully unstructured and non-hierarchical, I think it's one of the biggest one you have ever seen.
I think it was easily a magnitude more than I would have guessed was the biggest simulation out there.
Thank you.
All right, let's see. Any more questions? We have about 10 more minutes. Or maybe everything is clear at this point. All right, why don't we end early then? Let me first just go over to my slide here and remind you that this mini symposium has 3 sessions. This was the first one. And the next one is coming right after this, after a break. But I guess if we end now, it's going to be a 25-minute break. So 16:55, 4:55, we start the next one. And that would be, I believe, chaired by Suzanne. And I will make sure to forward this question from the chat to the last speaker, so we remember that. But yeah, that's it then. And thank you for attending this first one. And I hope to see you all in the next session.